this is interesting. It says, show that this long, ugly expression is a multiple of 10x. Well, that's not something obvious right now, and maybe on the side we need to remember what we mean by a multiple. For example, 12 is a multiple of 3. That's because if I think of 12 in a different way, it is 3 times 4, or actually I'll write it as 4 times 3, so we can say that it's 4 threes, right? So 12 is a multiple of 3, which means 3 is a factor of 12, okay? Because that's what we mean here. So really what we're trying to show is that 10x is a factor of that thing right there. Okay, that's really what we're trying to get at. Well, it's going to help, since it's not obvious, it's going to help that we actually expand this all out. So this is another one of those times where it's good for you to get some practice here. Go ahead and I want you to simplify this. Expand this, so you want to actually do the squaring here and do the squaring here. And don't forget, you cannot just put the squared into the two pieces. It doesn't work that way. You actually have to take 3x plus 1 times himself by distribution. And the same with this one. And simplify that out. So start by simplifying that. I want you to do it yourself. Go ahead and pause right now. Okay, let's check your answer to the simplifying of this. Well, 3x plus 1 squared. Maybe on the side here, actually, in this space, I will do my expansion boxes. And if you can do it in your head, no problem. But a lot of us are still going to be working this way. 3x times 3x is 9x squared, and then times 1 is 3x, and then 1 times 3x is 3x. Remember, each with each, that's why we do this, and 1 times 1 is 1. So this gives me 9x squared plus 6x plus 1, and I also need to do x plus 2 squared. X plus 2, x squared, and 2 times x, and 2 times x is another 2x. You notice this is always the same for those two middle pieces because you're squaring something. You're not multiplying something by a different thing. And this leads me to x squared. 2x plus 2x is 4x. Remember, we're adding all the areas together. Plus 4. So let's do this now. I get 9x squared plus 6x plus 1 plus x squared plus 4x plus 4, and then minus 5 at the end. Don't forget this, minus 5 all by his lonesome there. Well, we have some like terms here between everything. So I have my 9x squared plus x squared is 10x squared. I have my 6x plus 4x, which equals 10x, and my 1 plus 4 is 5, and then my minus 5 at the end. Oh, and that looks nice, because this is equal to 0. So I have in the end 10x squared plus 10x. Now, isn't that a much nicer looking rule than the original one? And again, remember, form implies function. If I actually plug some number into this function, and the same number into this function, you're going to get the same output no matter what number you started with. So this is a much nicer looking one, I guess you could say. Fewer steps, right? Well, this is, of course, counts as completely simplified, but if I really want to show that it's a multiple of 10x, that means 10x is a factor, right? Can I take a 10x and remove it here? Well, you can see there's a 10x in both of these things. I want you to think backwards with me a little bit here. If I have a 10 in both of these, I could pull it out. It's like reverse distribution, and it leaves me with x plus 1, I think. Because watch. 10x times x is 10x squared, and 10x times 1 is just 10x. So it turns out that I've showed it's a multiple of 10x. And that's because I can see that 10x is a factor of that. I worked with the basic rules of algebra. Let's give you yourself one last one to do on your own to practice this concept, and then we'll quickly run through it together, and then we'll call it good. So make sure you have this written. And last one for today. show that 2x plus 5 squared minus 25 is a multiple of 4x. Okay, so do that one again yourself, simplify it out, and show that it is 4x times something else. Okay, go. Let's look at it. 2x plus 5 times 2x plus 5 is going to be 4x squared. 2x times 5 is 10x, and 5 times 2x is another 10x. Again, we know these have to be the same, and 5 times 5 is 25. So if I add all that together, I get 4x squared plus 20x, right? 10x plus 10x plus 25, but then I have that minus 25 there. And what I get here is 4x squared plus 20x, because these become 0, right? Plus 25 minus 25 is 0. So, one last step because of the multiple thing. Again, is there a 4x that can be reversed, like undistributed out of here? Well, I think I would have an x here, and then, let's see, plus 5 I think, right? 4x times 5 gives me 20x, and so there we go. I've checked off and shown that it is a multiple of 4x. A little mini lesson here about what we call consecutive integers. If you remember, the word consecutive means back to back or one after the other. So when I say consecutive integers, we're just talking about two numbers that are right next to each other, but integers. So like 2 and 3, or 11 and 12, or 100 and 101, right? Two right next to each other. So we're going to look at some properties of consecutive integers, and we can use kind of our ideas from form implies function to do this. So let's start out by we're just going to do a few examples and then call it good for today. That's the main goal of ours, okay? So we may want to explore with some numbers. It's always okay to explore with some numbers first. So the sum of two consecutive integers is odd. Well, why don't you try a few pairs on your own? In fact, for all of these, you can go ahead and pause and try out with actual numbers and at least convince yourself by using some examples first, okay? Okay, so I hope you've actually done some examples yourselves. I might come up with my own right now. Make sure that for yourself you actually have written down your own examples though in your notes. So let's see, the sum is odd. So let's just like 2 plus 3, let's use the ones I already came up with. 11 plus 12, 100 plus 101. 2 plus 3 is 5, 11 plus 12 is 23. This is equal to 201. I mean, I've got 3 examples, and they all end up odd. Now, obviously, I want you guys to think about something really carefully. In math, if we're saying, actually not just math, in general, if we're trying to say something's true always, it's not really enough to give like 3 examples. In fact, it wouldn't be enough to give 1,000,000 examples. We need a better way to actually really thoroughly prove it. And this is where expressions are very helpful. If I have a number, guys, now here's where we really answer the question. If I have a number n, let's say, what's an expression for the next, right, consecutive integer? The next one up. N plus 1. Right? If this is an integer, n plus 1 is the next one. So really what I'm trying to show is that n plus 1 is odd. Well, let's actually add this together. N plus, now the parentheses don't matter that much as far as the order, it's just to help you realize these are separate numbers, I guess. But n plus n is 2n, and then we just have that plus 1. Notice this isn't multiplying, so I'm not distributing anything. This is adding here, right? So really this ends up being 2n plus 1. What does this tell me, though, about answering the question? Well, let's remember something. Anytime something's multiplied by 2, that means it's even. I want you guys to remember that fact, right? Remember that n itself is an integer. And anytime I double something, an integer, right? Anytime I have an integer and it's doubled, it's always an even thing. It's always an even number. Well, if I have an even thing plus 1, Don't you agree that if I'm at an even number and I go up one, that's always odd? Okay? So an even plus 1 is odd. And there we go. I've proven it. I've shown that that's true. I'm hoping that that is understandable to you and it feels good. You know, like it feels complete to you, like that reasoning. I hope it does, because that's actually a really simple way of proving that this is true. Now it says, how about 3? Again, I'm hoping you've explored a little bit of just with some numbers here, but why don't we try some numbers ourselves? And it says 3, they have to be 3 consecutive integers still. So let's use the same ones. 2 plus 3 plus 4. That's equal to 10. Am I right? And then 11 plus 12 plus 13. How about that? That's going to be 23 plus 13 is 36, right? And then 100, 101, 102 is going to give me 303. Now this is actually kind of interesting because, I made a mistake. I was watching this the whole time. You guys might have caught me. 2 plus 3 is 5 plus 4 is 9. Because I know what the answer is supposed to be and 10 did not agree with that. So hopefully you can at least have an idea of an answer to the even or odd thing, right? Because this is talking about being odd. Well, look, this is odd, but that's even, but that's odd again. Oh, poo. That's not even or odd. But can we say anything else at all about the 3? You want to take a really educated guess, possibly, about it? Well, I want you to think about something. 9 and 36 and 303, at least I can tell they're all divisible by something. Not 2 though, like they're not even, right? That means it's divisible by 2. And odd means it's one more than an even number. But I think they are all divisible by something. Hopefully you see at this point they're all divisible by 3 actually. Let's actually get to an answer here using the same idea with my expressions. We've already seen that n plus 1 is like 2 consecutive integers. Well, if I'm doing 3 consecutive integers, what's the next one? N plus 1, and n plus 2. And if I simplify this, n plus n gives me 3n, and then 1 plus 2 gives me 3. Wait a minute, 3n plus 3. This actually is like our last example in the previous video about form implies function, where we're thinking about being a multiple of something. Notice there's a 3 here. If I factor it out, it actually is 3 times n plus 1. Guess what? 3 consecutive integers are not even or odd necessarily, but they are all divisible by 3. And this is actually a proof of that. Okay? So, divisible by 3 for that one. Now the crazy thing is, what is it that's always being multiplied by 3? It's n plus 1. And if you remember, n plus 1 actually is the middle number in our string. So if we take the middle number, this is always 3 times whatever the middle number is. It's because it's averages actually. Because if I take the average of 2, 3, and 4, we get 3. And 3 times 3 is 9. Watch. 12 times 3 is 36. 101 times 3 is 303. That's pretty cool, huh? And then the last one, we can't quite reason through the exact same way, which is why I included it here. The product of 2 consecutive integers is even. So if I want to show something about the product of 2 consecutive integers, well, we may try doing the same thing. Now, we can do, let's use examples again, and we'll just use the same ones. 2 times 3 equals 6. 11 times 12 equals, that's going to be 110 plus 22, so 132. And then 100 times 101, looks a little scary, but remember we're multiplying by 100, so actually it's just 101 with 2 zeros. So that's going to be 10,100. And again, our examples at least agree with the statement that they're all even. Well, how do I tackle this? it seems like if I do the product of a number, two consecutive integers, I get n squared plus n actually. And that doesn't seem to be that doesn't really seem to be super helpful actually. You know what I'm saying? Because it's not really convincing that they're even. Because remember when we say showing something's even, let's go back to here. We should be able to see that it's a multiple of 2 times something else. But we can be a little sneaky with this actually and work it out. Let's go back to here. Do you guys agree that if I have two consecutive integers, one of them is going to have to be even? Does that make sense to you? Because if you have two numbers back to back, two integers back to back, you go from one to the other. One of the two has to be even. So let's actually just rewrite this guy right here, and let's say this is the even one, and we'll call it 2k. And we're going to use k to represent like twice some other number. So for example, if the two integers were, like, let's use this example, 100 times 101, we can think of 100 as 2 times 50, that's why it's even. But then 101 is 2 times 50 plus 1, because it's just the previous one plus 1. So the breakdown of this looks like that. So if n is the even one, let's say, and we could say either one's the even one, but it's easier to say this one, well then this is the same as saying 2k plus 1, right? So we haven't lost any ground here. Now if I distribute this, well, in fact, actually, I don't even need to distribute this anymore. I think I can be done, because watch. Do you agree that this whole thing is still just going to be some integer, some other number, and it's being multiplied by 2? Because this is 2 times all that stuff. And remember, if anything is twice something, it's even, okay? So this represents twice the value of k times 2k plus 1. So because it's twice something, it's even. And that may seem weird to you or like a shortcut or cheating or something, but actually it's entirely sound logic, because there you can't counter argue that, you know, and it doesn't break apart. It's completely thorough. So there's just some fun examples that you're going to see when you're playing around with the lesson, and I just wanted to add that in there for you.